Today, we're diving into a theory that could solve one of the biggest puzzles in physics, superconductivity. And look, if we crack this thing, it could unlock technologies that would absolutely change the world as we know it. So let's get right into it. I mean, just start with that question for a second. It's a massive one, right? But the quest for limitless clean energy is one of the biggest drivers in science today. And it turns out the whole thing might just hinge on a single elusive breakthrough. Take a look at this. This is a tokamak fusion reactor. You're basically trying to hold a star in a box. To do that, you need magnets so powerful, they're almost impossible to imagine. But with normal materials, you'd burn way more energy just running the magnets than the reactor could ever make. So you see, the dream of fusion power is, at its heart, a dream of superconductors. And it doesn't even stop there. Just imagine a world with power grids that lose zero energy to heat. AI data centers that are unbelievably efficient. High-speed trains that literally float above the tracks. All of this stuff becomes reality if we can just master this one technology. So, what's the holdup? Well, it turns out the problem is deeper than you might think. For more than a century, our basic understanding of how electricity even works has been, well, a little bit broken. And it all starts with an idea that seems to make perfect sense. This is the Drude model. You probably learned about it in school. It says electricity is like a bunch of tiny pinballs, the electrons, bouncing their way through a forest of atoms. Resistance is just the result of all those little collisions. Simple, intuitive, makes total sense, right? Well, here's the kicker. If the collision idea is right, then squeezing atoms closer together should create more obstacles, and resistance should go up. But when we do the experiment in the real world, the exact opposite happens. The more you squeeze, the lower the resistance gets, sometimes all the way to zero. Our basic model isn't just a little off, it's completely backward. Yeah. So if the old model is wrong and the data is undeniable, we must be missing a huge piece of the puzzle. And this is where this new idea comes in and just flips the whole table. It's called the electron tunnel theory. And it says we've been thinking about electrical resistance all wrong. So, what on earth is an electron tunnel? Well, the theory says that when atoms get really close to each other, they create this shared network of pathways. And along these paths, an electron can just glide from one molecule to the next without any effort, without changing its energy level. It is literally the path of least resistance. This diagram really helps make it click. All those wavy lines are like energy hills and valleys. But the electron tunnel, that path from A to B to C, it's like a perfectly flat, perfectly smooth superhighway that connects all the atoms. No bumps, no hills to climb. Electrons can just cruise. And here's the huge, mind-bending idea. Resistance has nothing to do with collisions. Nothing. Instead, resistance is just the energy cost to get an electron onto the highway. It's the on-ramp fee. Once the electron is on the highway, the ride is totally free. Now, this is where it gets really beautiful, because this one simple idea, this concept of electron highways and on-ramp fees, it doesn't just explain superconductors, it can explain pretty much every material out there. Let's break it down. In an insulator, the highways are all broken up. They're dead ends. Electrons are just stuck. In a normal conductor, like the copper in your walls, the highway's there, but there's a gap. You have to give the electrons an energy boost to get them on the ramp. That energy boost is resistance. And in a superconductor, the local roads just seamlessly merge with the highway. There's no on-ramp, no gap, no fee. Electrons just cruise right on. This picture shows it perfectly. A normal conductor on the left has that barrier. Think of it like a toll booth you have to pay to get on the highway. But a superconductor, on the right, well, the barrier is just gone. The lanes merge. It's an easy pass lane where the toll is always zero. Okay, so the idea is simple, it's elegant, it's beautiful. But does it actually work? Does it hold up when you compare it to real materials? That's the million-dollar question, right? Well, let's look at the data. This theory lets us calculate a value called resisting distance, which is basically the size of that toll to get on the highway. Now, compare the theory's predictions to the actual measured resistance of materials. It's incredible. Look at diamond. Theory predicts a massive number, and in reality, it's a great insulator. Look at copper. Theory predicts a tiny number, and yep, it's a great conductor. The predictions line up almost perfectly. The theory even explains why temperature is so important. When materials are hot, like on the right, their atoms are all jittery and bouncing around, pushing each other apart. The tunnels get broken. But when you cool them way, way down, like on the left, everything calms down and shrinks closer together. It mimics the effect of pressure, and poof, the tunnels form and overlap. And that is why superconductors have always needed to be incredibly cold. And all of this brings us to the holy grail, a room temperature superconductor. What's so amazing about this theory is that it gives us a clear roadmap. It tells us we're not waiting for some kind of physics miracle anymore. This is now an engineering challenge. And if the theory holds up, the path forward is no longer a mystery. It's actually crystal clear. And there it is, the secret sauce, straight from the paper. To make a room temperature superconductor, you need to compress molecular distances. That's it. That's the whole game. Just find a way to get the atoms close enough together for those electron highways to form and merge. That's the only rule you need to follow. So the challenge is right in front of us. The only thing standing in our way is the natural force that pushes molecules apart. Sure, we can crush them together with insane amounts of pressure, but that's not practical for building a new power grid. The real goal, the next great engineering frontier, is to design materials and structures that actually pull themselves together. And that kind of leaves us with this final fascinating thought. What if this theory is right? What if solving the world's energy crisis isn't a problem of fundamental physics anymore? It might just be an incredibly difficult but solvable problem of molecular engineering. And maybe, just maybe, for the very first time, we actually have the blueprint.